right, welcome everybody. We're glad that you've joined us for today's discussion about airtightness testing in buildings big and small. My name is Cheryl Saldanha. I'm a senior project manager at Simpson Gumpertz and Hager in the New York City office. I'm also a certified passive house consultant, and while I've run a few blower door tests myself, I'm pleased to introduce our speakers today and moderate today's discussion with these two very experienced gentlemen who have literally performed thousands of tests. I think we all know the concept of an airtight building envelope. It's been in our building codes for a while now in Canada and the US. But testing and hitting a specific target might be a little bit newer to kind of the wider market and industry. In the passive house world, though, airtightness is a fundamental criteria, and we need our envelopes to be airtight for durability reasons and to reduce the risk of condensation. And this testing is a critical quality control tool to help us achieve that goal. So joining me today, we have John Fassler. He's going to kick us off. He started his career as a custom home builder, actually, and then became involved with the city of Fort Collins in their home energy audit program. And he's now tested thousands of homes in Fort Collins doing these blower door tests. So with his presentation, he'll be introducing some of the basics of how to perform the testing, touch on the testing standards, and then some of the hiccups that can happen in the field and how to navigate them. And again, with a focus on smaller buildings. Then we have Torsten from RDH Building Science. He's a German-trained civil engineer, but over his career has gravitated towards advising clients on energy, building science, and how to design and construct high-performing buildings. And he has a wealth of knowledge in energy modeling, audits, codes, as well as this on-site performance testing. And Torsten's presentation is going to focus on testing bigger buildings, and he's going to share a case study on how he and his team had to perform tests, diagnose leaks, figure out repair recommendations, and then retest to show that they passed. So before I hand it off to John, a couple of housekeeping items. So just remind those of you in the audience today to please use the chat function, ask questions. This is a valuable opportunity to ask these experts your burning questions, so please don't be shy. And we have two presentations. The presentations themselves will be back-to-back, and then we'll have a moderated discussion at the end. And with that, I will hand it off to John to kick us off.
Thank you, Cheryl. John Fassler here. And yes, I've done thousands of tests on existing homes. And what I'll focus on today is passive house testing for single family residential. So to that point, the basics of it is, I've done tests anywhere from 1,000 square foot or 100 square meters, as we would more appropriately say, up to 600 square meters or 6,000 square foot. So we're right in that, but all single family homes. So in that range is what I've tested in. And then Torsten will touch on much bigger than that in his presentation. As most of us probably know, passive house requires that 0.6 ACH 50. It's a nice, concise standard. And I'll just talk a little bit about that and what the challenges can be in that, especially in meeting this ISO 9972 standard. ISO 9972 is the standard that Passive House has gone with, and it's the worldwide recognized standard for blower door testing. I do have a link here to Passipedia, which anybody can go in and find that in Passipedia. It's good to be able to have a reference source, I think. So the first thing I want to talk about to this is that volume calculation. As a former HERS rater, I know the volume calculation for a HERS rating can be all the way outside of the building, very basic calculation. For Passive House, we are talking about room-to-room calculations. You're not going out into the window opening things like that. It really is just the basic finished surface to finished surface calculation. And so it's a little too easy to make your job easier. You would make the volume bigger, but we want to avoid that. We want to adjust the area or the volume inside the building. I use automated testing software for all of my blower door tests. A lot of that comes from my QA background. When I see a manually entered test, I question it often. And so these are your three options that I know of for sure: TechTight, Fantastic, and rCloud. TechTight is a energy conservatory product, and Fantastic is RetroTech. Can be tough sometimes to get a test that is compliant with ISO 9972. So I do like to always state that plan on multiple tests, especially if you've got windy conditions or things like that. With ISO 9972, they've got a method 2. That's going to be your tests that you're going to be doing in a preliminary, probably right after windows are installed, but after all air barriers are on. Little note of warning: be careful with air barriers. If they are eventually going to have drywall on, they will not be as robust. And I have had air barriers blow off during preliminary testing. So they really have to be attached robustly for that preliminary test. And then the one that really matters is that method 1, which is the test with the building under normal operating conditions. And in that test, all we're blocking off pretty much is the ventilation, the ERV or HRV for that. I have a little note down here under wind, and I will talk more about that later on. So just to look a little bit about your two options here, this is the rig that I like using the most. The picture on the left here is the RetroTech blower door fully open, and that can go up to 6,400 CFM or 3,000 liters per second in air movement. And so that is going to do almost any single family passive house out there. It's hard to imagine. And even when I do testing on existing homes, I think I've had in 10 years, I've had 2 homes that a fan that can reach 6,000 CFM was not able to reach 50 pascals. So, and then over here on the right, we have, you can see that tiny little hole. I don't know if you can see my cursor there. That is, that will measure down to 4 liters per second or 9 CFM. So I can't imagine how tiny that house might be that might leak at that smaller rate. And then just to make sure we're representing at least the 2 options I know of, this is the same setup using the Minneapolis blower door system. These are 2 very great options. I've used both of them, and they will measure down very accurately into those ranges that we need to get into for passive house. So to talk a little bit about preparing the house for that preliminary air leakage test, filling all P-traps. Plumbing P-traps seem to be one of those things that really catch people by surprise. And you'll get a lot of air leakage through that the plumbing waste part of the building. So those are very important to have sealed or just filled with water. Sealing access doors is really important. A lot of time access doors are not in their permanent stage, and so taping those off is very legitimate during that preliminary stage. And then the last thing is sealing all mechanical ventilation. Now, most of the tests I've done, the mechanical ventilation system has not been installed when I have been in. So usually that's not an issue, but this is a good way to do it. I'll just go ahead to my next slide, because once we get into our final air leakage test, that is, we've got the same things, but one of the things we want to be careful of is that all supply and exhaust fans are off. And I have seen a lot of testers going in and they're using they're turning on fans, which exhaust fans are going to skew that test. A 40 CFM exhaust fan will skew that test by about 40 CFM. It's really competing with your test. And it's arguably skews it in your favor if you want a low number, but it's not allowed. And so other than that, it's close and latch all access doors. We don't want to use excess or use more tape. We want them in there using used condition then, or in the condition they'll be in during normal operation of the building. And of course, close and latch all exterior doors and windows. I've found that bladders are much more reliable than tape for sealing off an ERV. And I actually buy these playground balls from Amazon. They're $3 or $4 a piece, seem to be very tough and reliable. And so very, very inexpensive way to seal these off very solidly. And so that's the way I've come to go with those. So all that being said, I think it's good to talk about different jobs I've done. And I think one of the most interesting things is, where do you, if you pass your preliminary test, where do you end up? And this house, I don't have a picture of the house. I took a picture of Pikes Peak in Colorado Springs instead. But this house started out at 0.37 ACH 50. Pretty moderately sized house at 2,000 square foot to 220 square meters. So at 119 CFM 50, fairly airtight, looked very good as far as the ability to pass at final. But then over here on the right, I've got the final test results taken straight out of the RetroTech report. And you can see we hit 145 CFM. So we were actually 20% higher at final than we were at preliminary. So it's a good lesson, I think. Don't get too comfortable. It seems like that is a very typical thing that we'll see a little bit higher at final than we see. And I think 20% might be a good number to count on for where you might end up at the end of construction. So the other thing I find, this goes into my next point that I really think is, to me, one of the biggest challenges I've seen in our blower door tests, and that is windy days. These two graphs, I think, give such a great visualization. The graph on the left here was a test that I did on a windy day. This was done on 27th of October, 2022. And you can see the lines are just all over, even baseline. If you can see my cursor there, these numbers here, around 0, you can see baseline is just going all over the map. Very difficult to complete a test. And I actually, I did get a test. I did get a number, but I got all the warnings that said, okay, not compliant with ISO 9972. So I talked to the contractor, said I can come back tomorrow. Weather forecast was great. That graph on the right then was the test that we did the next day. So 24 hours apart. The lesson is, look at the weather. Really, if there's a way to move the test to a calm day, move the test. So these are the warnings or the messages then kicked out by Fantastic, our RetroTech software, and you can see we've got all these warnings and we're out of compliance in all these different ways. And then, okay, yay, test is in compliance the next day. So that's where we want to be. However, and I did also want to just talk about this. I think the multi-point test, this is the beauty of it, is that it is going through. It's correcting, it's taking averages. Really, the test results on that windy day, although they were out of compliance, they were still only 2.5% different than the test that was in compliance. So I think it's still a very good thing that Passive House requires that it meet the ISO standard. But I think you can also feel comforted in that, if you can't get that test done, if conditions just aren't permitting it, there's a likelihood that test done on that windy day could be okay and could work. Although technically for Passive House certification, you are going to be required to get a test that's in compliance. Want to talk a little bit about air leakage testing or finding air leaks. Sorry. Infrared, at least in the energy auditing world, is commonly thought of as the silver bullet that's just going to solve everything. And as you can see in these photos, it really was. We had a day where it was nice and cold outside. It was warm inside the building. We can see very easily these air leaks coming in. The problem is that very often we've got pretty equal temperatures outside to inside. And when we have that, we won't get these nice infrared pictures at all. So to me, infrared is a great tool on the right day, but a very frustrating tool on the wrong day. So nothing at all to rely on, I would say. It's the lesson from infrared. On the other hand, we have smoke, and smoke is much more of my preferred method. I will pressurize the building and I've tried multiple smoke devices. If anybody has any questions or wants some resources, I can tell you what I've used. I can tell you that I'm not happy with any of the smoke devices I've found so far. So if anybody has any smoke devices that work better, I'm very open to that too. You can see in these photos, even in a still photo, you can see that this the smoke is being pushed right out of those cracks. And this is where air leaks happen too. The framer was there the day that I was looking at this, and he said, "Oh yeah, you found those so quickly." And so I always know to go to that transition from ceiling to wall when I'm looking for an air leak. We'll see if this works. Oops. Yeah, there we go. This is a quick video. So I have, I'm outside with my camera, and someone is inside with smoke right on the edge, and the building is being pressurized. You can see that smoke coming out. So this is a test that's typically done with a high volume smoke machine. But in this case, this was done with just a small smoke pencil. So very effective way to find air leaks. I also found on this job that staples, every one of these staples seemed to have a tiny leak out of it. Hard to say whether that's productive or not, or something that somebody really wants to fight through. But it is interesting to find those and maybe correct for it on a future job. So all that being said, I think the things to take home from this are that automatic testing software can be challenging, but it does provide that nice professional report. Multi-point testing is required. A single point test, though, is very good for a preliminary test, and I always just do a single point test when I'm doing the preliminary test. That way we can go around and find leaks and diagnose much. We have more time for that. Be sure to get that volume calculation correct. Air leakage, like I said, happens at transitions. Tapes, people need to be good with tapes and use them and make sure they're really contacted on clean surfaces. Weather factor, that's something I just can't reiterate enough, that if you've got a super windy, gusty day, you're probably going to have a tough time getting a compliant test. And the second to last bullet I have here, as far as experience, I've worked with a lot of contractors and some of them multiple times. Almost all of them have challenges on their first project. But specifically, one of the contractors I'm working with right now in Fort Collins, I just tested their fourth house. First time through, they come out at 0.3 ACH 50, no challenges. First one, we were at 0.6, just right on the line. And so they really have nailed it and dialed it in. And so there's really not a lot of, I don't think there's a substitute for experience in this. And then the last thing I want to just talk about briefly is I've done two projects that did not meet 0.6 ACH 50. They've called in AeroSeal. AeroSeal both times came in and said, "Oh, we've got it. We nailed it." And they came in at, I think, 0.4. And then when I went back and test, it was just barely at 0.6 for both of these. And so use aero barrier, but use it with caution. There's a lot of other reasons, like not knowing for sure where it's hitting in the air barrier. So that's everything I have to say, and I'll take everybody's questions in the chat.
Thank you so much, John. That was a great introduction into airtightness testing. And honestly, most of the things that you said and that are relevant for small single-family dwellings, they are still relevant for larger buildings. And we will talk about larger buildings in my presentation here. So my name is Torsten. I'm with RDH Building Science, and my presentation here today is going to focus on an amazing project here in Victoria on Vancouver Island, British Columbia, Canada. But before we go there, a quick disclaimer. So everything you are going to see here in the next 25 minutes or so, this is really, it's for education, it's for training. So if you are taking, certain suggestions that I'm coming up here today with, just take it with caution and really apply it to the right circumstances. As always, make sure that your codes, your regulations are being followed. So, but let's start with my story about the airtightness testing for this particular project. So it is a $200 million student housing project that we are going to talk about. And it consists of two buildings. There's the building at the top. It's called the Building A, very creative name. And then the Building B at the bottom. The Building A at the top, which is the center of our story here today, is finished. The students moved in, and it has a very large institutional kitchen, and it serves about 9,000 meals a day. And that is one of the reasons why this project is not just one of the largest passive house projects in Canada, but also one of the most complex projects, as you can imagine, with such a large kitchen being part of that project. So it was designed by Perkins-Will, and it's being built by Elliston Kinetic. It's a joint venture by Elliston and Kinetic. 800 students are going to live in those two buildings once both buildings are completely finished, and both buildings are going to be certified as passive houses, and are also being certified for the LEED Gold standard. The center of the story and of this whole presentation here today is airtightness. And I will focus on the building at the top. We performed 7 airtightness tests throughout the construction process in order to rest assured that when the final day, the day for the final test came, and we knew we can hit the airtightness target for the building. So we started with a mock-up testing. Before the building even, hit the ground, we had this mock-up built. And the idea was that all of the transition details, all of the details that are relevant to the air barrier performance are somewhat they found their counterparts in this mock-up. So you can see here, we have our wall roof transition details. We have all the mechanical and structural penetrations through our air barriers simulated here. You see 2 different types of windows, the curtain wall window on the left and the punch window on the right. So those transition details, corners, you see overlaps, you see insulation attachment clips, and so on and so forth. So we try to design this mock-up with the idea of having most, if not all, airtightness relevant details incorporated into this mock-up. Because the mock-up is, very small, and obviously the idea was to make it as airtight as possible. We got away with our very small single-family dwelling passive house fan, and in the process of the test, we found a number of deficiencies, and really the amazing part of this process was that we had all the relevant consultants and the contractor on site while we were doing the test. And we were able to discuss the findings and the details, and we were able to come up with suggestions, modifications, and a lot of those discussion points and the proposed changes made it into the construction documents, and we were able to change some of those details to just so that we knew that the things that didn't work well here are going to work well at the real building. So just a short video showing that one of the mechanical penetrations didn't work well, so there was discussions on what's happening there, and we were able to find the culprit and redesign the detail. So from there, we moved on to test number 2. And for the first time, we started testing at the actual real building. And we chose a section of the building, a multi-purpose room, indicated here with the red circle, for a couple of reasons. Most of the actual main building was obviously still under construction, but this section down here on the level 1 has actually a lot of curtain wall. It also has mass timber as a building material and main structural component. So that there are a lot of very unique details that we were very curious about how those details are working. And I have a couple of screenshots just showing you. On the left-hand side, you see the section, and on the right-hand side, you see the detail kind of enlarged. So you see the mass timber suspended floor, some mass timber beams, and you can see, if you look carefully enough, the air barrier wrapping around this beam and then tying it into the curtain wall. Another detail kind of shows the top of this section, how the parapet and the roof are coming together. Again, our main focus was how this relatively complicated air barrier transition detail is going to work. And then just one last detail showing how the curtain wall is tied into the air barrier strategy. And because the building was still under construction and most punched windows weren't even installed yet, so we needed a temporary wall to isolate this portion of the building from the rest of the building. So the general contractor, EDK, built this temporary wall for us and an opening where we could install our equipment. And similar to John's presentation, we used smoke and we used infrared to analyze to diagnose the performance of the air barrier. So you can see there my coworker Eric on the boom lift on the outside using a smoke machine and applying smoke to the depressurized building. And for us to kind of see where is the smoke coming in. We did both. We had smoke on the interior while pressurizing, but it really depends on the conditions. Sometimes one method works better than the other. So we found in this particular case, it was easier for us to locate the leakages while depressurizing and applying the smoke from the outside. We also used the infrared camera to assist with finding the leakages. But you can see here, the smoke was really the big helper here on that day. You can see tons of smoke coming in, which pointed to a weakness in the curtain wall system. This curtain wall consists mostly of fixed glazing units, but at the very top, there are operable glazing units. And they have to do with the natural ventilation strategy for the whole building. And clearly there was something that wasn't working as well as we had hoped. And when we looked into the details, we found that this kind of primary gasket that you can see here indicated by the arrow, there were some inconsistencies, and this gasket just didn't create the right pressure to create a right air seal. So when we went to basically back to the drawing board and had discussions with the manufacturer and also the installer, they realized that they needed to modify some of the details. And you can see here on the left-hand side, that is the detail as it was when we did the test. And they needed to, basically they came up with a solution that included adding a somewhat rigid custom-made corner block to support this gasket. And just going back here, once this was installed and when we retested, and we tested this on site, but also they tested it in the factory, and they basically could confirm that this change of detail helped to basically eliminate the air leakage around the operable parts of the curtain wall. Other than that, we found the typical usual culprits. On the right-hand side, you see some fish mouths, and on the left-hand side, some tenting when there were some transition details. We had the contractor and all the subtrades on site when we did the test, and everyone could see how their product was performing in the real world. So there was a lot of discussions, and we found ways to help everyone understand what's needed in order to get the quality that was required to push this airtight building. So from there, we moved on to test number 3. This time, we wanted to test the punched windows, and we moved up to level 3 as indicated here with the red circle. Again, the building was still very much under construction, and that's the whole idea. For a mid-construction test, you want to find any kind of deficiency before it is too late, before all the windows are installed, or before the same detail where you find potentially a deficiency has been completed everywhere else in the building. No, you want to find those deficiencies early on so that the modifications and the corrections can be applied to all the details that still need to be implemented. So again here, the contractor built temporary walls for us so that we could isolate our test zone from the rest of the building, which was still very much under construction. And again, we used infrared, we used smoke. And you can see here, we did some corrections right at the time of the test. The contractor really wanted to understand how correcting some of the deficiencies, how this is impacting the measurements and the smoke ingress right at that moment. But there was something else that we found. As indicated here by this photograph, there was quite a bit of smoke ingress at the hardware for all those punched windows. So imagine this project. It has hundreds of windows, and we are doing this small zonal test, and we are seeing smoke coming in at those hardware penetrations. Obviously, there was concern, and also we were not able to answer the question whether that could be a deal breaker. Is the sum of all those leakages, is this going to cost us our passive house certification because we may not be able to meet our required airtightness levels? So the only way to really get down to the bottom of this and find the answer to the question, is this a deal breaker, was by adding a test that we had not planned for. Basically, we needed to come up with test methodology that allowed us to isolate this particular problem from the rest of the building and then analyze whether that is going to be so significant that we really need to go back and fix those deficiencies on all the windows that had been installed up to that point. So what we did, we came up with a testing methodology that involved 10 of those punched windows as shown here. There was still scaffolding in front of the building, so it was relatively easy to access those windows. And we developed and made a test chamber that fit exactly and perfectly onto the window frame. And you can see here the ducts and the small fan and the computer that assisted in this testing. And basically the basic idea was that we wanted to test this window in under two different conditions. On the left-hand side, it shows the condition as is. Yeah, you see the unsealed handle that was the location for the smoke ingress that we just saw on the previous slides. And on the right-hand side, you see the same handle, but this time it's sealed. So we measured each of those 10 windows twice. And the results can be plotted into this table here. You see column 2 and column 3 have those highlights. One is the unsealed condition, the other one is the sealed condition. So we were able to calculate how much the unsealed condition, how much air leakage it adds over the sealed condition. And we were able to take this and then extrapolate this test result to all the windows that are installed. And we were able to calculate that those leakages only contributed to about 1% of the total air flow that was allowed for this particular building. And you see here highlighted a reference to 0.4 air change rates at 50 as a target. And we will get back to this. So this particular building has a 0.4 target instead of our typical 0.6 target as we know it from passive house projects. And again, I will get back to this. However, once we calculated that this particular problem deficiency only contributed to 1% of this allowed budget, so to speak, we knew this is not going to be a deal breaker, and we were able to basically calm everything down, and we knew that we can focus on other parts of the building. And then for the very first time, we moved on to a mid-construction that involved the whole building. So by now, many months later, all the essential components that have to do with the air barrier were installed, or the windows were installed, and so on and so forth. And we were able to test the whole building to see how we are doing when compared against the requirements. So we installed 2 fans at this lower roof access location, and then one other fan at the very top roof access location. And this is how it looks like when you bring all your equipment. So it's a lot of equipment, but imagine if this building would be built to just standard code construction performance levels, we would have 3 or maybe even 4 times the amount of equipment that would be needed to depressurize and pressurize a large building like this. So it's also, passive house is not just good for comfort and for greenhouse gas emissions. It is also good for the testers and their back problems they may have, because we just have to carry way less equipment around the buildings. And this is how it looks like when some of the equipment is installed. You can see in the background on the 2 fans installed. In the foreground on the right, you see the computer that controls those fans. And then kind of in the middle, you see all the hoses and Ethernet cables that allow the fans to talk to each other and to the computer, and the hoses to ensure that the pressure conditions are the same throughout the whole building, and so on and so forth. So it takes quite some time to set up a large building test like this, and some last minute preparation steps before we hit the power button. And here we are seeing the test results. So highlighted is the average between the pressurization and the depressurization test. And you see we came in at a 0.19 air change rate at 50. So everyone was very happy about this result, because we knew we are on the right track. Our project specific target was 0.4. So we had quite a bit of wiggle room. And it really showed that all our effort and hard work in tracing and tracking down deficiencies, addressing those deficiencies, having discussions with all the consultants and the contractor involved, and modifying details when necessary, really had played out well for this project. And then a few months later, it was time to test the whole building for the last time. At least that is what we thought. So we chose the same locations for the fans because that worked out really well. You can see here us preparing for the test. But when we tested, we came in at a very disappointing 0.51 air change rates. Again, from a passive house perspective, this would have passed because 0.6 would have been the threshold. But our specific project went through a very intensive value engineering phase where it was decided that, among many other items that were looked at, air change, the airtightness of the building was used as one way of essentially saving cost. By making the building more airtight, we were able to reduce insulation levels elsewhere, and we were able to modify other passive house relevant components and basically save project costs. But in order to make this happen, we had to tighten up the building, and we had to aim for a 0.4 and not for a 0.6. So without meeting the 0.4, we would not be able to meet all the other passive house relevant criteria, like the PER, for example. So a 0.5 was not an acceptable result. And we were suspicious straight away and started really focusing on components that have not been installed at the mid-construction test. And the main culprit that we were very suspicious about were those, we had 4 of those very large overhead doors. And at the time of the mid-construction test, those doors hadn't arrived on site yet. So those openings were had seals, temporary seals. And we found the culprit after not very long. We found that this seal at the very top of the head of the overhead door did not fully engage. So you can see that brush seal, there was a gap. And not just another photograph kind of indicating the vertical brush seal performed really well, but the horizontal brush seal at the very top had gaps in certain locations. And we did the math, we calculated whether that was indeed the culprit. And yes, our math showed us that those kind of deficiencies were sufficient enough to basically push the test results to a 0.5. We looked at all the shop drawings and we discussed what can be done about this. There was no time and no way to have those doors uninstalled and replaced. They came from Europe, so there was no way to do this. So we needed to find solutions that could be implemented as a fix to those installed doors. And the general contractor came up with a solution that worked very well, as we will see in a couple of minutes. Basically, we installed a secondary seal once all the flashing and everything was installed, and that brush seal basically reduced the air leakage to acceptable levels. So it was then time to retest the building, because obviously that initial final test result wasn't acceptable for this particular project. So we did our depressurization test, multi-point, as John pointed out earlier, and you can see it's a perfect correlation. So all good here. We had a correlation of 0.99. But when we did the pressurization test, you can see straight away something happened that looked quite different. And you can see the correlation dropped from 0.99 to 0.4 and made this test result not acceptable. So something happened at higher pressures. As you can see, the error indicates when things started, up to 40, 45 Pascal, things looked actually really good. And then at those higher pressures is when we suddenly saw the pressure drop and the airflow go way up. So the first thought that we had was something started opening up at higher pressures. And we sometimes see this, especially with buildings that have a lot of mechanical equipment, a lot of motorized or spring-loaded dampers. Sometimes those dampers get overwhelmed at higher pressures and start opening up. So this is a very, very complex building when it comes to mechanical systems. So we needed to find this particular damper that started opening up at higher pressures. But you can see there's a lot of equipment, a lot of heat recovery ventilators, a lot of motorized dampers, and so on and so forth. Just another shot here showing all the mechanical equipment installed on the roofs. However, almost by chance, we ended up finding that something else caused this problem. And it wasn't on the roof, it was down here, as indicated with the circle. And it ended up being a door that behaved exactly the way that we just talked about. Something opened up at higher pressures. What had happened was, on the day of the retest, this final test, all the locks, or many locks, were replaced in preparation for the handover of the building. And this particular replaced lock, something went wrong when they replaced this, and it didn't fully engage. And when we increased the pressure over 40 Pascal, the mechanical door closer got overwhelmed, and the door started opening up, causing exactly what we saw on our graph. The pressure dropped and the airflow went way up. So it was easy to fix this problem. And there we are. Our final test result for building 1 ended up coming in at 0.22 air change rates combined. That is the average between pressurized and depressurized. And this, and I really want to emphasize this kind of test result would not be possible without just showing RDH here, but I'm not talking about ourselves. This is Marlene and myself here. It was because of the dedicated folks at the general contractor, and especially Mac and Jordan here shown in those circles. Those two were the dedicated, basically air barrier bosses. They were responsible for this complex air barrier system that was installed with the many transition details. And only because of those two and their dedicated check on materials and the specifications and all the transition details and the sequencing and the checkups of the substrates and so on and so forth, only because of their constant checking and the constant follow-up with the substrates allowed this project to essentially come back with a test result of a 0.22. And this brings me almost to the end of my presentation. This is a photograph that was taken on the same day of the retest. You see beautiful Victoria late summer evening. And you see a little bit of how beautiful this design is with those exterior shades. Yeah, and that brings me to the end of my presentation. If you have any questions, please put them into the chat, and otherwise I will hand it back over.
Thank you, Torsten and John, for your insightful presentations. We got a lot of great nuggets of wisdom. So we're going to keep the conversation kind of going here. John's just going to dial in a second, folks. Oh, here he comes. So he's connecting with his audio. Just give him a moment. Hi, John.
Hello, everyone. Can you hear
There
me?
we go. Yes,
Okay.
all good.
Here we go.
So I was just thanking you for your presentation and the great wisdom that you shared. I think there were a lot of good insights. And so I want to keep the conversation going and ask you both a few questions here. So I think both of you touched on the idea that, one single test at the end really isn't enough. And there's a lot of value in doing sort of preliminary tests along the way. So I'm curious, when you're kind of approached, let's say by, an owner or maybe a contractor for a proposal, how do you go about estimating the number of tests that might be appropriate when you're preparing that proposal?
John, do you want to go ahead?
Sure. I'll take a first crack on it. For small buildings, for residential, it seems like experience is probably the biggest determining factor. That if I've got a new builder, often we're going to do 2 preliminary tests. And the length and price of those tests is not going to vary a lot. It's just the second test. So effectively just adds just one more test to the program, to the process. And then the finals, in my experience, have been pretty good. Again, very difficult to set a price. The biggest variable there has been weather, where I've had to go back because we had a weather day and go back and perform again another test. And that is largely for me communication and just letting the contractor know that we could have some unanticipated extra costs for return trips. Torsten, you have anything to add to that?
For larger buildings, it very much depends on the complexity, and again also whether the contractor had previous passive house experience, whether they had experience with airtight buildings. So we have had projects where one mid-construction test was sufficient, but we also had projects like the one that we just talked about, where we needed, multiple tests in order to have everyone on the same page when it comes to airtightness. So it really depends on the complexity and the experience, as John just said.
And then building on that, how would you approach the setting of when those sort of mid-construction tests occur? Are there certain construction milestones maybe that you're looking for to kind of do a test either before or after?
For larger buildings, so there are a couple of things that play into this. Obviously, the air barrier component and the transition details, they need to be done in order to be tested, but we also want to, especially when you have large complex buildings, the same detail that you're going to test will repeat itself thousands of times afterwards. So you can't wait until all this is done and then find out that there is some problem with how the detail has been done. So the way we address this in the project that we talked about, we just had test chambers, large test chambers built, so to speak, in order to isolate the test zone from the rest of the building, and we're able to, see how those details are working, and the lessons learned got applied to all the ones that needed to still be built.
For smaller, for residential buildings, what I've done, I largely have always let the consultant on the project drive when the test is going to happen. In the early days, we did some tests before windows were installed, and but it was also kind of doing it as a hobby. It gets expensive to do those extra tests, and it's kind of guaranteed that you're really going to have a big increase or possibly substantial increase in numbers if you're going before windows are installed and maybe a very airtight seal over that window. So ideally, I'd like to see windows installed and every possible window and door installed. Once in a while, there's a custom door or something like that that is not there. And hopefully that won't impact the test too much, but all those little variables, getting those as complete as possible is really good for that preliminary test and before drywall.
Yeah, that makes a lot of good sense. Thinking about the passive house consultant on the team as well. I mean, are you guys doing the volume calculations? Are they doing it, and then you're checking it in some way? Like, at what point does that kind of happen?
Again, it depends. For us here at RDH, we are sometimes the building enclosure consultant as well as the passive house consultant. Sometimes we act as the certifier. So personally, if I'm responsible for airtightness test of a passive house, I leave it up to the passive house consultant, whether that's our own team or an external passive house consultant, to calculate the volume, just because that volume is being used within the PHPP calculations anyways, and it needs to be accurate. So I would always rely on the passive house consultant.
Second that. Same here. We use trust the consultant for good numbers. And I have measured one building room by room, and it is an arduous process. And so I think the architect or designer has a much better tool using plans to come up with that measurement for volume calculation.
And then, John, this is a question to you. So when you're testing single family homes, have you ever had to test one with a ventilated attic? And do you have any advice on doing a test of a house with a ventilated attic, or do you just, recommend it because it can be more difficult to make it airtight?
So most of the testing I do is not passive house testing, and so most of the testing I do has a ventilated attic, and so that ceiling plane, and for most energy audits that we do, that is the biggest leak in the house. And so I would say to that, yeah, it's just we kind of know where that leak is. We can, on the right day, we can verify with infrared. We can sometimes verify with smoke. But almost all older homes, we can very much justify vacuuming out all the insulation and using spray foam, unfortunately, to seal all the air leaks. And we often see over 50% air leakage reductions in the whole house by eliminating that connection to the ventilated attic, which is basically outdoors. So does that answer the question, I think?
Yeah, that's great. And then, Torsten, for you, large multifamily buildings, maybe taller buildings. I'm curious if if we have a certain number of floors, when you have a tall building, stack effect comes into play. So is there a certain number of floors that you're maybe limited to because of the stack pressure that builds up in these tall building tests?
Stack effect definitely becomes something that you need to consider, especially in the planning process. So in theory, there is no limit when it comes to airtightness testing. Yes, stack effect, the taller the building, the more you will have to deal with stack effect. But you basically essentially need to ensure, once you know what your stack effect is, you need to correct for the stack effect and ensure that the whole pressure, top and bottom, at the whole building, top and bottom, is pressurized or depressurized to whatever target pressure you have, plus the calculated or measured stack effect pressure, so that there is not a certain part of your building that's not experiencing the same conditions. So there are ways to overcome this, and Passive House International has published a really great document describing all the methodologies that can be used for large building airtightness testing, especially with considerations for high rises and stuck effect. So I highly encourage people to take a look there.
Do you remember the name of that document, just in case there's folks that aren't familiar? They can kind of go look it up.
I will find this and put it in the chat.
Okay, thank you. Next question, and this came up in the chat during the presentations about AeroSeal and air barrier. Curious how often you see folks trying to use it to make a building pass the air test requirements, and are there situations where this is a valuable tool, or situations perhaps where it's not?
I have had a number of projects where this product has been used, but I have to say none of them were Passive House projects. I have not seen anyone involved in Passive House projects trying to rely on this product. We were able to, using mid-construction tests, we were able to basically get rid of deficiencies and achieve the level of airtightness with our dedicated traditional air barrier. And the projects that were non-Passive House and that used aerosol, often those buildings had failed their particular targets, and now there needed to be some kind of a fix in place, and so they chose to use aerosol. Sometimes it worked, sometimes it didn't work. So again, for Passive House projects, I highly recommend to have your dedicated air barrier doing the job, and not something that that is being applied and creates an air barrier somewhere in within the assembly that is less defined as a dedicated air barrier. John, you probably have some experience.
Yeah, I've done 2 projects, some Passive House projects, where we have they did not meet the standard at preliminary or at final, and both of them called in Aero Barrier. Aero Barrier came in and claimed to have reduced the air leakage to far below 0.6. But then I still have to go back and do an official test, and both of those barely passed when I did. So, less than a month apart. So you couldn't really necessarily say that it was degradation of the product. I believe it must have something to do with whether they're unmasking the windows or not when they give that final number, or something like that. But so, if I think if you've gotten to final and you're not meeting the standard, sometimes that might be the only option, is to try Aero Barrier, but do so with caution. And I'd highly recommend avoiding it as much as possible, because it came up in the chat. What's it going to do over time? Is it failing that quickly? If it's degrading in a month, then that's really a bad metric for it. But I think Aero Barrier should be used with caution. And we do have builders here in town who use it regularly for code-built houses. I'd like to go back to those houses after a few months and check and see what those are doing. So.
Yeah, and along those lines, I think that's a question that we all have is, we do these tests pretty close to, when the buildings are first occupied, and they're performing really well from an airtightness standpoint because we've just tested them. But have you ever gone back to a building several years after occupancy and retested to confirm, that they're still achieving, some level of similar airtightness?
Yeah, I had a couple of projects where we needed to go back to Passive House projects for other reasons, but where retesting the airtightness was then just part of that scope. And both of those projects, the airtightness levels were more or less the same as tested at the end of the construction process. And I think it has a lot to do with the fact that usually, for passive house projects, the components, tapes, and so on and so forth, they are high performance materials. So they are designed to last. And that really shows in those retests that I did. And I believe PHI, Passive House International, did similar projects where they retested a number of buildings and and those buildings all tested very similar to what they had been tested at the end of the construction process.
And similarly, I've been back on one project. My friend Andrew Mitchler, who does a lot of passive house building, lives close by, so we're able to go up and use his house as a test. And we've seen very little, a little bit of an increase, but I do think he's had some problems with the HRV, and some of the ducting has been out of place. So I think it has more to do with a single point of failure, or even temporary failure in that case, something that's just not in place when we were there. So it seems like it's holding up very well.
Yeah, it makes sense. It all starts back at the sort of design phase and material selection, choosing durable, reliable materials as part of the air barrier system, and then it will have that performance long term. The next question, and this kind of also came up in the chat a little bit, is about floor door technology and air testing technology. Familiar with these sort of ultrasonic and using these acoustic testing equipment to potentially locate air leakage sites. Any insights from you guys on sort of advances for tools that maybe are making testing easier, faster, or different technologies like that ultrasonic tool?
Or talking about airtightness equipment, we recently had to replace a number of our cloths for that are being put over the frame when you install the blower doors, and we bought some of those ones that have now wind dampening built right into the cloth. So and we found the test on single family that we did, it worked really well even on windier, more gustier days. Those results were way more stable than what we typically see in the typical approach. So that's an advance for maybe smaller buildings, and then we see for larger buildings, especially on the software side, we use Retrotech. On the software side, there's constant innovation and advancement. So new features are being introduced, and many of them are very useful and make those complex tests easier. And especially when it comes to troubleshooting, it's easier to find which fan is out of bounds and not doing what it is supposed to do. So we see advancement there, especially on the software side.
That's great to hear, Torsten. I've been debating whether to buy one of the wind cloths or not, and I've gone back and forth on whether it's worth it or not. It's might push me that direction. And then I think ultrasonic is something. It sounds great, and I'm very curious to learn more about it. Have not used it. It seems a bit on the expensive side when we talk about residential air testing, air leakage testing. There's quite a few jobs, looks like, in order to pay for that. So I have to go out and check the appetite for that increased level of information. And could it be worth it or not is a good question.
Yeah, we have been very successful with the traditional diagnostic tools, smoke machines, smoke pencils, infrared cameras. But we are also definitely open to explore new tools that are available, and will probably do so with some of those new technologies that are entering the market.
Yeah, and just like with any sort of new technology that's entering the market, it usually is more expensive at the beginning, and as it gets sort of adopted and more and more, the price can come down. So yeah, certainly interested to see what else is out there. Next question is related to code requirements, and if you have any insight into kind of blower door code requirements that may be coming up in different jurisdictions.
Well, I guess because we are talking about passive houses, and that passive house standard, is referencing a certain testing standard, ISO 9972, and I guess that even though there are many different airtightness testing standards available out there, I guess the actual standard is always driven by the passive house requirements, and there might be some updates coming, but so far I think we are all relying on ISO 9972.
I agree. I recently did some testing, not even for code, just for a remodel. So a lot of jurisdictions require, when you do a remodel, they want to test before and then after. And they're only testing to make sure you didn't make the building worse. In that process, I looked at the ResNet standard a little bit. The ResNet standard is kind of funny. You can do a single point, very quick test and just add 10% to it, and then ResNet allows that. So it's always interesting for me to see the ends of the scale. But from passive house, where we're doing pressurization, depressurization, multi-point testing, and clear down to what I would term the bottom of the barrel. Apologies to ResNet for that. Single point testing, add 10% and go. So.
All right, and we're running low on time, but I have one more question, and that's related to, preparation of the building for testing. So there's some guidance from Passive House and some standards, but I'm curious from your experience. I know, John, you mentioned in your presentation using, for example, that bladder, that toy, basically to, put into the duct opening. I'm curious if there's other sort of improvements that you can think of that might want to be included in some guidance document to help with preparing for a blower door test.
Okay, go ahead.
So I'm now speaking large buildings. Preparing for an airtightness test is actually quite an exercise. Going back to the building that I used for my presentation here today, we have 12 HRVs there, and not all of the HRVs are continuously running, depending on which zone and within the building they're serving. There are, differences in their schedule. So it was an exercise or the planning had very much the mechanical consultant involved, because we needed to understand which of the HRVs we are allowed to seal and which HRVs needed to stay unsealed. So it has less to do with gadgets that might help preparing the house. It's more like the planning process for larger buildings. It is not just that the tester, him or herself, usually it's teamwork, because you need to fully understand the mechanical systems as well as the building enclosure in order to come up with a test plan.
I would agree. I have not really seen much in the way of new technologies, but just the thought process of what we're trying to get is the air leakage rate of the building under normal operation. And so taping doors shut, things like that are just not allowed for that final test. And I do see some of those kind of attempts once in a while, going for some unrealistic. And also, I think people overestimate the effects of a tiny little pinhole here and there. So it is, passive house is a different animal than more leaky houses, but it is one little hole in here and there or around the blower door itself is not going to have a big effect on the test.
All right, guys. Well, thank you so much to Torsten and John for wonderful presentation and very insightful question and answer period here. Thank you to our audience for your participation through the chat and some of the questions you gave. They were great. So with that, we're going to sign off here and hope to see you maybe next week in person for those of you who will be in Denver. Take care, everybody.
Thank you so much, everyone, for listening.